Hi, this is Steve Richardson with GSI Environmental, coming to you live from my guest room to share an overview of a recently funded ESTCP project entitled Innovative Plasma Technology for Treatment of AFFF Rinsate from Firefighting Delivery Systems. This project is led by Dr. Selma Mededovic at Clarkson University, DMAX Plasma. She serves as the principal investigator and is the coolest plasma destruction expert I know. The project is also supported by Dr. Tom Holson at Clarkson University, DMAX Plasma. He's the lead for PFAS and co-contaminant analyses. I'm Steve Richardson with GSI Environmental, and I serve as the field demonstration technical lead. And my colleague Poonam Kulkarni serves as the lead design and field engineer for the project. We're also fortunate to have Dr. Michelle Crimmy on the team, who will support our technology transfer activities. So let's just jump right into the problem statement. There are a large number of fluorine-containing AFFF delivery systems at DoD facilities. In fact, there are about 4,000 within the DoD's aircraft hangars and on firefighting vehicles. There are environmental concerns with AFFF use. As we know, these fluorine-containing AFFF foams contain perfluorinated, polyfluorinated alkyl substances, or PFAS, which are difficult to treat. There are limited and ineffective treatment technologies. Granular activated carbon is the most common treatment method, but it has its limitations, particularly with short-chain PFAS. And then there's waste generation. Current technologies require varying levels of off-site treatment and disposal. So what's needed? As DoD facilities switch to non-fluorine foams, cost-effective technologies to treat AFFF rinsate from firefighting delivery systems such as aircraft hangars or aircraft rescue firefighting vehicles, AFFFs, is needed. Our objective is to demonstrate and validate an existing mobile plasma treatment system for the treatment of large volume PFAS containing rinsates. So what is plasma? Plasma-based water treatment uses electricity to convert water into a mixture of highly reactive species, it's called plasma, which have the ability to rapidly and non-selectively degrade recalcitrant organic compounds. There are a wide variety of benefits associated with this technology. One is that it generates a wide variety of reactive chemical species, most importantly aqueous electrons. There are also hydroxyl radicals and other radical species that are produced. It's capable of treating a wide variety of compounds, including PFAS, as well as other co-contaminants. And then the plasma process requires no chemical additions and produces no residual waste. So how does the technology work? Well, plasma is formed by discharging high voltage that's applied between suspended electrodes that are located above the water surface and submerged grounded electrodes. Those high voltage electrodes for generation of plasma are depicted by these gray triangles in the schematic on the right. And then the schematic below, or the top view, you can see the stainless steel strips that serve as grounded electrodes. One of the important components of the plasma reactor are gas diffusers that are positioned along the bottom of the reactor for bubble formation. Down on the bottom is a picture of the prototype reactor. So the mechanism for PFAS destruction is really based on leveraging the properties of the PFAS molecules, which are surfactants. By bubbling argon gas through diffusers at the base of the reactors, we can produce bubbles that concentrate PFAS at the headspace or argon-water interface. PFAS molecules are exposed to those reactive species in the plasma, and then the dissolved reactive species generated by the plasma drive reactions within the water column and break apart the carbon-fluorine bonds within those PFAS molecules. So let's jump into a quick video of the plasma in action. So that was a pretty cool video, huh? But the big question that remains is, does plasma really work for the treatment of PFAS? And the answer is yes. We recently conducted some laboratory experiments with the prototype reactor on a variety of different PFAS impacted water sources, and you can see what those different water types look like: varying turbidity, TDS, and other water quality parameters. And what we discovered was that by and large, PFAS and PFOA concentrations were reduced to less than 70 ppt, that's the EPA's health advisory level, within 1 minute of treatment. Anecdotally, we saw treatment through some visual observations. If you look at the picture on the right, you can see that when gas is bubbled through the untreated sample, foam is created at the water surface, which is expected. But when you do the same thing to the treated sample, no foam is produced. If you're curious or interested in more information about this study, I would recommend that you give our ES&T paper, which the reference is right there, a review. We further tested the technology in the field by creating and constructing a mobile plasma treatment trailer, which was recently demonstrated at a fire training area at Wright-Patterson Air Force Base. Approximately 350 gallons of PFAS impacted groundwater were treated at a range of flow rates up to 1.1 gallons per minute. And you can see the treatment trailer in the figure on the right. Results of the field demonstration were very promising. We achieved significant removal of PFOA, PFAS, and other long-chain PFAS in a short period of time. If you look at the graph on the right, you can see we achieved 2 to 3 order of magnitude reductions within one cycle of operation. Each cycle represents one pass through the reactor. Concentrations that were achieved at the end of the study were below the detection limit of 9 ppt. We achieved similar results for precursors or the fluorotelmer sulfonates. For short-chain PFAS, longer removal times on the order of 3 to 6 cycles through the reactors were required to achieve concentrations of less than 9 ppt. Of note, however, PFBA and PFBS saw fairly poor removals over the experimental duration. This is because it's difficult to get these compounds through the water column up to the headspace water interface where they can interact with the plasma that's generated. Addition of simple surfactants such as CTAB have been found to facilitate this transport and improve treatment efficiency. So the technical approach for this project will focus on site selection, which will guide us through AFFF Rinsate characterization. Once we get a sense for the composition of the AFFF Rinsates, we'll conduct treatability testing at Clarkson University and optimize the reactor to suit that water chemistry. We're also going to look into pre-oxidation testing to see if there is value added to treating some of the precursors with an oxidant prior to plasma treatment. We'll then make the necessary trailer modifications and then move into a field demonstration at the selected field site. So that about wraps up the overview. If you have any questions, please reach out to the project team. I know Selma, Tom, Poonam, and myself would be happy to answer any of your questions.